We have another Taylor polynomial problem here. So when I see a third degree Taylor polynomial, what I'm thinking about is my main definition where I'll stop it at the third degree. It says about x equals 0. So I'll go f of 0, f prime of 0, x minus 0 to the first over 1 factorial, f double prime of 0, x minus 0 squared over 2 factorial, f triple prime of 0, x minus 0 cubed over 3 factorial. So it helps me to write that down. And then if I read a third degree, that means I'm going to need a third derivative. So here's my original function. I'm going to take the derivative of that 3 times. So we know the derivative sign is cosine, derivative cosine is a negative sign, and the derivative sign is going to be another cosine again. But then each time you got to times it by the derivative of that angle. So the derivative of 5x was the 5, and then that 5 carried down, the derivative of that 5x was another 5, that 25 carried down, the derivative of 5x was another 5. So you just have to remember your chain rule and times it by the derivative of that angle right there. And then f of 0, let's see, that's when we take 0 plugged into the original functions. That'll give us the sine of pi over 4, which is radical 2 over 2. F prime of 0, we take 0, plug into this guy here. So we'll do cosine of 0. We're going to get the cosine of pi over 4, which is radical 2 over 2. But then you got that 5 in front of there, and then the x carries down. The second derivative will plug in 0 right there. So sine of pi over 4 is radical 2 over 2 again, but you got a negative 25 in front of there. X squared over 2 factorial carries down, and then plug in 0 for the third derivative. Cosine of pi over 4 is radical 2 over 2, but you got the negative 125 in front. X cubed and the 3 factorial carries down. So if you could just use your main definition, remember your basic derivatives there, and then find that Taylor polynomial, these problems are worth 9 points. That part A, just this right here, is worth 4 out of the 9 points right there. So we could definitely make sure we're getting as many points as we possibly can. Now for part B, it wanted us to just find the coefficient of x to the 22nd. So if you look at the patterns a little bit here, I guess you don't have to write down all of them and take 20 some derivatives right there. But what I notice is that they all have a square root of 2 over 2 in them. So square root of 2 over 2 is going to be there. And see how I had x to the third over 3 factorial, then x to the fourth over 4 factorial, x to the fifth over 5 factorial, which means when I have x to the 22nd, which is what they're asking for, it's going to be x to the 22nd over 22 factorial. Like those numbers are always going to match. And so I got that. And then also this was x to the first, this was 5 to the first. This was x to the second, that was 5 to the second. That was x to the third, this is 5 to the third. And so when I go to the 22nd, that's going to be 5 to the 22nd. So that stuff I got pretty easily. And then what hung me up a little bit, I was like, I'm not sure whether it's going to be a positive or a negative. And I do know the signing is going to go positive, positive, negative, negative. And the derivative of cosine is a negative sign. It's going to switch it back to a positive again. And then that's going to forever alternate. So I got a little bit overly cautious. I'm sure maybe some of you think of a different way to see that pattern and stuff there. But for right now, I just kind of did plus, plus, minus, minus, plus, plus, minus, minus. And I was like, hey, that was x to the first, that was x to the second, because the first one didn't have an x attached to it. And so I just kind of went all the way down the line. And when I got down to what would have been that x to the 22nd, I did have a negative right there. So if you have a better way to do that, I think I came up with a better way one time, although it's not popping in my head at the moment right there, but we can discuss that individually if we need to there. But see, the coefficient of that x to the 22nd is just the number stuff in front of there. And so that's what they're meaning for part B. So that was worth 2 points just for part B. Letter C has this LaGrange error bound. And I'm going to explain how to do this in a LaGrange. I already explained how to do this in the LaGrange error bound video, but I'll explain it again right here. So this is the formula for the LaGrange error bound. Don't worry about all the letters or anything like that. It just says you're going to maximize the n plus first derivative. So if they said n is equal to 3, because it's a third degree polynomial, we're going to maximize the fourth derivative. So I did the derivative of this guy here. The fourth derivative ended up being this. And remember, your sine graph just forever fluctuates back and forth between that 1 and negative 1. And then so your amplitude, you know, like your basic sine graph, it'll go up to 625, down to negative 625. Your maximum of that thing will be a positive 625. So that's where that 625 came from. And then your x is that number right there, the 110. Okay, and then also I'm using LaGrange error bound because it tells me to use LaGrange error bound, and when that notation kind of looks like they're just doing the error between the original, the true value, and the estimated value from your Taylor polynomial right here. When you do this x minus c, the c is the center, which is equal to 0. The x is the 1/10 in there. That's where I did 0.1 minus 0 to the fourth power because my n is 4. My n is 3, so 3 plus 1 gave me the 4. And then again, my n is 3, so 3 plus 1 gave me the 4 factorial on the bottom. And then it's a little annoying I had to do this without the calculator right there, but I knew this is 1/10 to the fourth, so I dropped that down to the bottom, made it 10 to the fourth on the bottom since it was 1/10. 4 factorial, 4 times 3 times 2 times 1 to get to 24. Without the calculator, there might be a different way that you see how to do this, but I knew that 625 was 5 to the fourth, and I rewrote this 10 as 2 times 5 to the fourth. That was 2 to the fourth times 5 to the fourth. Then boom, those 5 to the fourths cancel out, but then I still had to do 16 times 24, so I did a little bit of old school multiplication to get this 384 on the bottom right there. And then they said show it that's less than the 1 over 100. We know that this is true since that 384 is bigger than that 100 right there, but you don't have to write that down. So there's the LaGrange error bound, really not showing up all that often right there, but if something pops up, you know, similar to that, we kind of just practice this problem and the other problem I showed you in that LaGrange error bound video, and we can be good at that. And then the last one, and then all that trouble, letter C was only worth 1 point right there. So as you got to decide whether it's worth your time to, you know, work with that. We're going to master everything else first. And if we got some time to just make sure we study these a little bit, the couple problems that we have over it, then we'll focus in on that. But regardless of what you thought about letter B or letter C, letter D is actually a quite easy problem, okay? And again, it's been my experience on these problems, when you have a string of things like this and you see a derivative notation later on the problem, you're meant to take the derivative of those few terms. If you see an integral notation in the problem, you're meant to integrate those few terms right there. So that's what we're going to do. They're always going to use different letters. Don't ever worry about that. But we want to write a third degree Taylor polynomial. All right, so third degree, which means our final answer, we want to be an x to the third as the highest exponent. We don't want to be an x to the fourth or anything like that. So since this has f of t, I rewrote these few terms right here in terms of t. And then I stopped it at the squared one because I know when I integrate the square, it's going to give me the cubed, right? So you could integrate it with the t's and then plug in the x, and then you have your x's in, minus plug in the 0, those are all go away. Or you could just kind of integrate it all with the x's right there. But when I integrate the radical 2, you're going to get, like, technically it's radical 2 over 2 times t, but then you plug the x in and it's going to become x's again. So you could just integrate it with the x's, and this would be like t squared over 2, which is x squared over 2, and then that's where the 4 came from, and this would be like t cubed over 3 or x cubed over 3 to get that 25 over 12, and then we have that third degree Taylor polynomial. So I just want to stress, if you know your main definition from the videos, know how to do some basic derivatives, there's 4 points right there on letter A. Maybe we have trouble with letter B. Maybe we have trouble with letter C. But the integral, we could all integrate those few terms right there. You see an integral, do an integral, and then that's worth 2 points right there. So if you get letter A and letter D, boom, I mean, you got 6 out of the 9 points right there. And we don't have to be perfect. There's a significant curve to this test. We just try to master each problem and do the best we can, get as many points as we can. But, you know, if you're getting as many points as you possibly can, that's gonna be really good for us. All right, so just keep working hard, and thank you. Juice.